B.2, efficiency analysis of binary search. Yeah, so let's look at the details. Yeah. Diagram for binary search. Now we are familiar with the basic process. When we do comparisons, we always compare the given key with the element that is the median of the current ordered array. Current, yeah, because we do a lot of eliminations. After we eliminate the maximum number of elements, we can say they cannot be the given key. Yeah. So then, the current ordered array. All right, let's draw the diagram. Yeah. So this line segment represents an ordered array. Yeah. Our first comparison, we compare it with the median. Regarding the median, I need to say something about the median. Yeah. Because here we use the concept, median concept. All right. So what's the meaning of the median? Exact median. Yeah. Because our data size M can be even and odd, right? Yeah. Two cases, n even or odd. When n is odd, the meaning of median is clear, right? The element right in the middle, only one element. But when n element is even, then which element is the median, right? Because there are two elements in the middle, they have the same, similar position, position-wise, they both are near the middle, right? Near the middle. All right. So in that case, we need to define the meaning of median clearly. Yeah. All right. Because two elements in the middle, one left, one right. Yeah. Yeah. Equivalent. Yeah. Because we cannot favor one over the other, right? How can you say one is a better one for the median than the other, right? Yeah. So these two, then people call this one left median. Two medians, left median and that one right median. Right median. Yeah. But the left median, yeah, because if you don't want to always specify left median, right median, right? Yeah. So that's not convenient. Yeah. So if you do not say left or right, left one is the default. This is the default median. Yeah. Yeah. So then you do not need to, yeah. So separate, even or odd, left, right. People don't want to say that much. Yeah. Yeah. Just use the left median as the default median when n is even. Yeah. All right. Another thing you need to beware of, that is, in computer science, the meaning of median different from people use in math. In math, the median is slightly different, because in math, the left median, you have two, right? Yeah. So left median, yeah. Oh, how to erase? Yeah. And the right median, there, they define the average of left median, right median as the median in math. Okay? Yeah. Left median plus R median divided by 2. That's the math way. We cannot take this formula. In computer science, this formula will cause a big problem. We don't want to use this formula. Why? Because if you use this definition, then the median will not be one of the elements in the array. Because this value is not an element in the given array. But we want the median to be one of the elements in the array. Median must belong to the array. But the math way, the median does not belong to the array. So we cannot use the math definition. Okay? So we need to use our own definition. All right. Yeah. Now we do the comparison. First round, second round, and so on. Keep doing until we do our last comparison. Yeah. Because first we need to compare. We need to consider the worst case. How many comparisons do you need to do for the worst case? Yeah. So let's answer this question first. Yeah. After first comparison, you drop approximately 1/2 of your data. Yeah. Not exactly, may not be exactly, but approximately 1/2 of your data. So our data size is reduced by 1/2 after first comparison. Then, after second comparison, we reduce another 1/2, yeah. And we keep doing comparison. Yeah. After, let's say, K comparisons. Yeah. After K comparisons, yeah. What is the data size after we make a K comparisons? Yeah. Here, we do this chart. After comparison 1, comparison 1, the data size, comparison 2, data size. After K comparisons, the data size becomes n over 2 to the kth. Right? Yeah. All right. So then, next question. How do we find appropriate K such that after K comparison, we can stop? We reach the end. We do not need to do one more comparison. How can we find that number K? That's the important point for our worst case, because that K corresponds to the worst case. All right. Yeah. So here we need to find some criteria. Yeah. Yeah. So think about the situation after the last comparison. What is the data size after last comparison? After K comparison. All right. If the data size of the K comparison is strictly less than 1, then you do not need to do any more comparison, right? Strictly less than 1, that means you have at the most one element to be considered, right? Yeah. So no more split. Because one element, how can you split one element, right? Yeah. Nobody can split one element. Yeah. So when the data size is strictly less than 1, no more split. That means you have to stop. Okay? You have to stop. All right. So now we use this inequality as our stopping criterion. Stopping criterion. How do we decide we should stop? All right. Yeah. That is this inequality. This inequality tells us Now, what's the meaning? Yeah. The left-hand side part, after k comparisons, the data size is strictly less than 1, so we should stop. Yeah. The right-hand side inequality, it tells us, after k minus 1 comparisons, the data size is greater or equal to 1. That means you may need to do one more split. Because that data size, greater or equal to 1, may cover 2 elements, right? Yeah. So that line segment, greater or equal to 1, yeah, it could cover 2 elements. There is a possibility that the length of that line segment can cover 2 elements. So you need one more split. Yeah. So these 2 inequalities give us the stopping criteria. Yeah. So we need to figure out this k, the k that make this inequality occur. Yeah. All right. Yeah. So let's simplify this inequality. Yeah. Then we take log base 2. Yeah. So we want to find the range for k. Yeah. Yeah. Log base 2. Yeah. All right. Yeah. And our goal, we want to find, oh, what's wrong? So messy. Yeah. So the software, today is yeah, so bad today, the software. Yeah. All right. Yeah. So now we need to derive the worst case formula. All right. The worst case formula, so based on what we have here, yeah, so we get this one. But there is a problem. We know k is an integer. K is an integer. Log base 2 of n is not an integer. That's the problem, right? Yeah. So then we need to fix that non-integer problem. Yeah. All right. So here, another thing. So why I do more work? Because look at this less than sign, strictly less than sign. Yeah. Because strictly less than sign, that does not give us the best approximation. So we want to improve this strictly less than sign. So how to improve? Yeah, that means in this inequality, how to improve on this strictly less than sign. Okay, all right. We make this improvement. Yeah. N strictly less than 2 to the k, then n minus 1 should be less than or equal to 2 to the k, right? Yeah. That's the way we improve it, plus 1. Yeah. Because a is an integer strictly less than power of 2 to the k. Yeah. So n plus 1 has a chance to be equal to 2 to the k. Yeah. So we improve it by 1, okay, plus 1. That's the improvement part. All right. Yeah. Then, this time we get improved version because both places we have less than equal case. All right. So we improve the inequality slightly. All right. But the next thing, log base 2 is not an integer expression. Log base 2 is not an integer expression. So we need to convert the log base 2 part to integer expression. Remember, we use floor function, ceiling function to do the conversion before, right? That counting the binary digits, that question. We use the floor function, ceiling function to convert non-integer expression to integer expression. Here, this is the situation we need to use floor function or ceiling function to convert log base 2 expressions to integer expressions. All right. For the lower bound, we take ceiling function. Now, moving up, rounding up. For the upper bound, we rounding down. We take floor functions, rounding down. Yeah. All right. So after that operation, conversions, we have two formulas. The first formula, the lower bound part, we take ceiling function. The second one, the upper bound, we take floor function. So there are two possible answers we can use. Yeah. But these two expressions are the same, are equal. These two formulas are the same. Yeah. Expressions slightly different, but mathematically, they are the same. Yeah. And if you want to prove it, you can apply mathematical induction to prove it. Yeah. This formula can be proved by mathematical induction. Okay? And this formula also given in our textbook, in appendix. In appendix, you can find this formula. Yeah. All right, now, our conclusion. The conclusion, what is the best case? One comparison. Best case, yeah, one comparison. The worst case, these two formulas, one of the, yeah, so you can pick any one you like. Yeah. One of the two. Yeah. The first one or the second one. Yeah. That's the worst case formula. Yeah. Then next question, what's the average case? Yeah. After we get a best case and a worst case, what is the average case? Yeah. Can we say the average case is just the average of best case and the worst case? Yeah. In general, no. Yeah. In general, you cannot say that. Yeah. Only in special case, you can say it, right? Yeah. The special case. Yeah. But the general case, you cannot say. So for our binary search, the answer is no. The answer is no. No. You cannot say that. The average case, more complicated. You need to calculate. It is more complicated. Okay, all right. Yeah. So next, our next question, how to calculate the average case efficiency. Yeah. We need to do some work. Yeah. We need to combine all the possible cases to get an average case efficiency. Yeah. Yeah. Here, I want to use a simple example. Yeah. When n equals 7, so for this simple example, yeah, so let me do the detailed work to show you how to calculate average case efficiency. All right. B.3, average case efficiency of binary search. Yeah. Here, we use the n equal to 7. Why 7? Yeah, so if you ask me, oh, yeah, still messy. Yeah. Yeah. The messy thing, yeah, let me try this. Yeah. Let me get out of my current presentation and then get in again. Yeah. And try to remove the messy part of this PowerPoint slides. Yeah. So let me quit the current presentation. Then get in again to see if we can do better. All right, so now I quit. Okay, all right. Then start it again. Yeah. And I change my pen color. All right. Yeah. Now let's see if it is better. Yeah. Analysis of average case. Yeah. 7 elements sorted array. Why 7 elements? Because it's 2 to the third minus 1. Power of 2 minus 1. This special number would give us a complete binary tree. The binary tree we draw with 7 nodes, it's a complete binary tree. So that's the reason, yeah, because it's very convenient. Okay, so that's why I pick this special number. Yeah. All right. Yeah. So now let's draw the binary tree corresponds to the binary search. Yeah. What is the first comparison? We compare the given key with node number 4. So first comparison is at the node number 4, so we put it at the root node. Yeah. All right. Yeah. Yeah. So here I talk about probability P. Yeah. Related to our linear search. Remember the linear search, if the given key is in the array or not, then there is a probability P. Yeah. Yeah. But here we skip that part. Okay. So we do not consider probability P. We just assume the given key is in the ordered array. That's that case. Yeah. Because after that, we can use the similar way we use in the linear search to cover when the given key is not in the array. Yeah. All right. Yeah. So the first comparison occurs at the root of the binary tree. So node number 4 is at the root. Yeah. And to get a match at the root, we need a 1 comparison. So I put that little 1 there. Yeah. Then 2 branches of this binary tree, a left branch and a right branch. For the left branch, our second comparison, based on the binary search, we need to compare V with node number 2. Node 2. Okay? Yeah. Similarly, right branch, we need to compare it with node number 6. So that's second level. So we need 2 comparisons. Then, the bottom level, 2 branches of node 2, so node 1, node 3. 2 branches of node 6, node 5, node 7. Yeah. Now you can see you get a complete binary tree. All the levels are full. Yeah. So that's the meaning of complete binary tree. Yeah. And the bottom level, 4 elements at the bottom level, we need 3 comparisons. Okay. Now we are ready to write a formula for the average case efficiency. Okay, yeah. Because this time we can use a fair way to combine all 7 cases. So you have 7 cases. Right? So V equals 1 of the 7 elements. So total you have 7 cases. So let us combine all these 7 cases in this way, average case way. Denominator, the total number of cases, 7. The numerator, yeah, so look at the formula, the numerator. Yeah. 1 times 1. Yeah. So why 1 times 1? Okay. Yeah. 1 times 1. The first one means the number of comparisons for the first level. Okay. Yeah. Number of comparisons. Okay. So the first level, 1 comparison. Second level, 2 comparisons. Third level, 3 comparisons. The second one, number of nodes in this level. The first level, 1 node. Second level, 2 nodes. Third level, 4 nodes, and so on. Then we, calculate. We can find the answer. 17 over 7. Yeah. And when you get a final answer, you use this fraction number as your final answer. Do not round it up or round it down. Many students like to round it up or round it down. Yeah. The reason is they feel, because you're talking about number of comparisons, right? Yeah. So in their mind, based on their understanding, they feel the number of comparisons should be an integer. Yeah. But here the question is the average number of comparisons. When you take average of certain number of integers, in general, you will not get an integer answer. So it is reasonable your average number is a non-integer number. No problem. Do not run it up, not run it down. Okay? Yeah. So that's, when you see average, you do not need to run it up or down. When you see best case, worst case, then we expect to have integer answer. Best case, worst case, it should be integer answer. But for average case, we do not expect to have an integer answer. Not necessary to have an integer answer. Yeah. All right. Yeah. Yeah. So that's the general way. Yeah. So although here it's a special example, so you can easily extend it to do any general example, right? Yeah. General example, you need to draw appropriate binary tree. Then you count the number of nodes each level, okay? Number of comparisons. Yeah. So then you write the formula for the average case efficiency. Yeah. Yeah. In your homework assignment number 2, I will give you a similar question. Yeah. Calculate the average case efficiency for the binary search. All right. B.4. Introduction to selection problem. Now we need to look at the general selection problem. So we did some special selection problem, but we also need to look at the general selection problem. The general selection problem, given an array and a positive integer k. Okay, the k number we want to use to find the kth smallest element. Yeah. Kth smallest element. Yeah. So that's the general selection problem. Yeah. Yeah. So there are several names for this k. Yeah. 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 Some official name, some formal name called a kth order statistic. Yeah. Formal name. Yeah. But many times people call rank k. The rank is k. Rank 1. Yeah. The smallest element, its rank is 1. 1, 2, 3, and so on. Yeah. Yeah. But just a name. Yeah. All right. How to solve it? Yeah. Some analysis of this question. Yeah. Yeah. The data, when we solve the general selection problem, so we expect our data is unordered. Definitely unordered. If it's ordered, too easy, right? Yeah, too easy. Yeah. Unordered. Yeah. All right. But the question is, should we solve the array first? Yeah. So when you need to solve the general selection problem, should we solve the array first? Because after we sort it, it's very easy to find the kth smallest element, right? Yeah. The answer is, if you sort it, you need to do this many comparisons in big data of n log n. N log n. Yeah. So that's the best we can do. Yeah. N log n. No. All right. Yeah. But if you just want to find the fastest algorithm that solves the selection problem, you do not need to do this much work. This work more than necessary. Because you do not need to do that much work. Why you need to sort it? You do not have to sort it. You can do less amount of work to find a solution. So that's the main point. Right? Yeah. That's the main point. The question is, what is the fastest algorithm to find the kth smallest element in a given unordered array? That's the question we want to solve. That's the general selection problem. All right. Yeah. To solve it, we need to apply divide and conquer. the title of this module 4, divide and conquer. So here we need to apply some very special divide and conquer way to reduce the problem size. Yeah. We want to reduce the problem size. Yeah. How to do the right way of size reduction. So that's the main technical problem to be solved for this question. Yeah. All right. Idea. Yeah. Divide the problem into two sub-problems. But the question is, in order to get better performance, better efficiency, the way to divide is very important. Yeah. All right. Yeah. Yeah. Because you can drop one of the sub-problems. Yeah. The case is small. After one comparison, you can make your decision. Yeah. You have two subarrays. You can make a decision. One of the two subarrays does not contain the given, does not contain the kth smallest element. Then you can drop that subarray. You reduce the problem size. Yeah. So that idea. Yeah. All right. Convert the original problem to one of the, yeah, because after that you do recursion, right? Yeah. So you recover the situation of the original problem. Divide and conquer again. You do recursion. Yeah. So the main step is how to divide the original array. If you can find a good way to divide the original array, so you're almost there. Because the remaining part, you just do the recursion. Yeah. Here you can see recursion is very powerful, right? Yeah. Yeah. So you do not want to lose the power of recursion. No? So powerful. So you only need to fix that divide step. Then recursion would do the remaining work. Yeah. Yeah. All right? Yeah. Right. So here, for this kth order statistic, let's study a little more. Because kth order statistic, you count from left, right? You count it from the left. Left. You do left counting. Yeah. But when you do right counting, because there is another way you can count, right? Yeah. From the maximum side, you do the right hand counting. So you have another different counting number, right? Yeah. So sometimes we need to look at from both sides, from left-hand side counting and from right-hand side counting. When we do eliminations, we can do left-hand side elimination. We can also do right-hand side elimination. In that way, we will have more chances, right? So we do not do one-side elimination. Yeah. One-side elimination, you would lose half of the chances. Yeah. The other side, we have a lot of chances on the other side. Yeah. So that's why we do both side eliminations. Yeah. All right. So elimination idea. Yeah. Two cases. Eliminate from the left end. Yeah. When we do some comparisons, after we collect enough information, we can eliminate certain number of elements from the left end. Yeah. Okay? All right. Another case, we can do elimination from the right end. Yeah. After some comparisons, we may have enough information to do some eliminations from the right end. Yeah. Both end eliminations. All right. Yeah. So here, the elimination from left end, elimination from right end. So we can reduce the problem sizes as much as we can. Yeah. Yeah. All right. Yeah. All right. Yeah. Then next, yeah, because the key step is this device step is the key step. So later we need to focus on the device step. Yeah. For the device step, then let me bring up that balancing principle a little bit, that idea. Okay? Yeah, data, yeah, because when we consider, we split the data, right? So this is the data split point. Yeah. We split the data somewhere in the middle. When we split the data, yeah, so that balancing principle tells us that in order to get better efficiency, we want to make our data as balanced as possible. All right? Yeah. As balanced as possible. Yeah. In other words, yeah, we look at the same question, but in a different way. The different way is we want to avoid the unbalanced data splits. Yeah. Yeah. So another way to view this question, avoid unbalanced data split. Okay, unbalanced data splits. All right. So what's unbalanced data splits? So your split point too close to the one of the two ends. That's the unbalanced splitting positions. So we want to avoid extremal or near extremal unbalanced splits. That's the idea. Okay, all right. How to make that happen? How to make that happen? Yeah. So when we do the divide step, we want to choose some cushion here. Left cushion, right cushion. Okay? Yeah. Because these two red circles we will use to avoid extremal unbalanced splits. Yeah. So how large is the left circle? How large right circle? We will find a way to make it, 30% of the data. Yeah, 30% of the data. Okay. So when we make our split, we can adjust our algorithm to make the splitting point in this part, in this middle part, avoiding 30% portion of the left or 30% portion of the right. So in that way, we can avoid very unbalanced data splits. That idea. Now, how to make that happen? Yeah. So how to make this idea happen? Yeah. We need to do a lot of work. So I delay that work a little bit, because we need to do a lot of preparation. We need to, do some relatively simple work before we can do this complicated work. Yeah, this work is, relatively more complicated. So we need a lot of preparation. Then we can understand the idea. Yeah. All right. Yeah. Now, before we do that, here. Before we do that, so let's do some preparation work. As a preparation, B.5, let's solve another interesting problem, that is find the median of 5 elements. Yeah. Another challenging and interesting question. Yeah. All right. And also, the solution of this one, its solution we will use it, yeah, useful, we will use it for the selection problem. Because selection problem, the first step, we need to apply this solution. Okay? Yeah. We need to apply this solution. Yeah. And when we apply it, we can avoid 30% portion from the left, and we can avoid 30% portion of the right part of the data. Yeah? So this solution can help us do it. Make that happen. Yeah. Yeah. All right. Yeah. So let me work on this example first. Yeah. All right. Question. Find the median of a 5-element array. We can assume distinct elements, yeah, for our convenience. Yeah. All right. And the data, still these 5 elements. That's our data. All right. Yeah. Solution. All right. First, let's recall how many comparisons do we need to sort 5-element array. Yeah. We just did that question in the first half. Yeah. To sort a 5-element array, we need 7 comparisons, right? 7 comparisons. Yeah. Let's recall a little bit. That number is optimal. 7 number of comparisons, that's the optimal one. Yeah. All right. But here, we only need to find the median. We do not need to sort it. If you sort it, you do more than necessary work. That means 7 comparisons, more than necessary. So you should do better than 7 comparisons. Okay? Yeah. So your target here, yeah, less than 7 comparisons. Because if 7, we just sort it, right? Yeah, sort it, then we pick the median. Yeah. All right. Yeah. So let's, yeah, because let's say 6 comparisons. Yeah. Yeah, because it's very hard to improve even 1 comparison. Here, we reduce the number from 7 to 6. That's a big improvement. Yeah. That's a big improvement. Yeah. So let's target this 6 comparison first. Yeah. If you can solve it with 6 comparison, then you can try 5. Yeah. But nobody can make it work. Make 5 comparisons. So 6 comparisons are already good enough. All right. Yeah. Yeah. Now, round 1. Okay. All right. tournament method. Tournament method. All right? Yeah, tournament method. Yeah. Round one. Yeah. So same thing as we did before. Yeah, let me repeat it. Yeah. Yeah. Because we can do it very fast. Yeah. First pair, second pair, all right. Yeah. Then let's draw our diagram. Yeah. This diagram. X1, X3, X4, X2. Then one element X5 here. Yeah. But we don't want to sort it. The question is, we don't want to sort it. Yeah. So we need to do something different. Yeah. Yeah. If we do the binary insertion, then it's the same as the sorting problem. So this time, we need to do something different. So round two. Round two, elimination method. Elimination method. Okay? Based on the given information, can we do some elimination here? Can we do some elimination here? Given method? Yeah. Yeah. So from the diagram, you can see, can you see there is some element that does not have any chance to be the median. So we need to find some element. There is no chance this element can be the median. All right. Here, so let's look at the median again. The median in this situation equals third smallest element, right? Or third largest element. Okay? Yeah. So which element cannot be the third smallest or third largest? We need to find such element. Then this element has no chance to be the median. Look at that question. That's the critical step. Critical step. All right. Look at this element, X1. Look at X1. We check one of the two questions. X1, can you see it has no chance to be the third smallest or third largest? One of the two. Yeah. So we'll look at the question from the two sides. Yeah. Yeah. The smallest side, the largest side. Yeah. All right. From the diagram, you can see X1 greater than 3 elements, right? X2, X3, X4. X1 is greater than at least 3 elements. How can it possible to be the third smallest? It is already greater than at least 3 elements. It has no chance to be the third smallest, right? Yeah. So from that observation, x1 can be eliminated. Okay? x1 is gone. No way x1 can be the median, so we should eliminate it from consideration. All right. But after elimination, so, the data is quite messy, so we need to clean up our data. So after the elimination, okay, what do we have? We have x2 here, x3, x4. x3 is greater than x4, x5 unknown, right? Yeah. All right. x5 unknown. Okay? All right. Yeah. So we can make our comparison. Yeah. Because this round, tournament round, we need 3 comparison. 1, 2, 3. Okay? All right. So this comparison is comparison number 4. After comparison number 4, between x2 and x5, one element is greater than the other, right? Yeah. Either x2 is greater or x5 is greater, but these two cases are symmetric, right? Yeah. These two cases are symmetric. So we only need to consider one of the two cases. So here we assume x2 is greater than x5. So x2 is on top. x5 is at the bottom. Yeah. All right. So comparison number 4, compare x2 and x5. Okay? All right. Yeah. Then, but we need to update our goal a little bit, right? Oh, sorry. Here, after we need to update the goal. Our original goal, find the median. Find the median, that is the third largest, right? Median is the third largest. But after elimination, x1 is gone. So after elimination, the median becomes, second largest. Because x1 is gone. Second largest in the remaining 4 elements, x2, x3, x4, and x5. So our goal, so we need to find the second largest in these 4 elements. All right. Yeah. Then, okay, all right. Comparison number 5. Compare x2 and x3. The larger one will be the first largest, right? In these 4 elements. The winner of comparison number 5 is the first largest. Yeah, so first largest left. Okay, all right. Then the second largest, the loser of comparison number 5, you compare with, so here, because for discussion, X2 or X3, which one is larger? Symmetric case, right? The symmetric case. Yeah. So if you want to make your discussion a little easier, we can assume X2 is larger. Okay? Yeah. We can make X2 is the winner. Yeah. Because two symmetric cases. All right. X2 is the winner. Then comparison number 6. Yeah. The two candidates for the second largest. Candidates for second largest. Yeah. Because X2 is gone. So X3 compare X3 and X5. Yeah. Yeah. The candidate. Yeah. 3 and 5. Yeah. But not X4. X4 is smaller than X3. So X3 has a chance to be the second largest. X5 has a chance to be the second largest. But X4 has no chance to be the second largest. Okay? So the last comparison between X3 and X5 and the winner is the second largest. But the second largest in these 4 elements. Okay? Yeah. So that one is the global median. Global median. Yeah. Yeah. You include all the elements, the global median, the final solution. Yeah. Final solution, so you need 6 comparisons. Look at this solution. Okay? Look at this solution. Hope it's not too hard to understand. Okay? Yeah. The first round tournament method, then second round elimination. You need to eliminate X1. After elimination, you need to update. The median becomes second largest among the remaining 4 elements. Then, to find the second largest in the remaining 4 elements, then you do 3, yeah, because between X2 and X5 you need to do 1. Then after that, you need to do 2 more. So total 6 comparisons. All right, yeah, so that's the, yeah, so we complete this example. Yeah, yeah. So next time, yeah, because our next class, our main topic review for midterm. Yeah. So we will spend most of our time next class, going through all the possible questions for the midterm. Yeah. So after that, so then we will continue this topic and the remaining of this module 4. Yeah. After module 4, then module 5. Yeah. So module 4 and module 5 content belong to the final. Okay. Midterm, you do not need to worry about module 4 content. Okay? So you only study the first 3 modules, module 1, 2, 3. Yeah. Yeah. And last 2 modules, that's for the final. Okay? Yeah. All right, that's it.